Alright guys, so this is going to be a video over rotational kinetic energy. I'm kind of new at this, trying to do the videos in the video, so we'll see how this goes. But to start with, what I'd like you to do, I'm going to have this video, and this first one, what we're going to do is we're going to take three different objects. So we've got a sphere, a solid disc, and a hollow disc, or a hoop. And we're going to let them go. And what I want you to do is I'm going to let it go, and I want you to predict which one will get to the bottom of the hill first. And then I want you to tell me why you think that. All right? I know that you can't directly tell me, but just do your best. Like think it through. Which one do you think is going to hit the ground first? Do you think they're all going to get to the bottom first? If you do think they're all going to get to the bottom, we're talking about right here. If you do think they're all going to get to the bottom first, why do you think that is? All right? So let's take a look and see what happens. Whoops. Take a look and see what happens. If I hit play, okay. Let's see if we can back that up. Oh, can't back that up. We just got to apparently keep going. All right, let me try it again. So let's look at it again. Boop, 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 boop. All right, right here, which one gets down there first? It's a little bit tough to see, but the sphere here is definitely in the lead, followed by the solid disc, followed by the hoop. And I've got a video in slow-mo to demonstrate this again. So let's try showing this in slow-mo. In slow-mo, it's a little bit easier to see. That sphere takes out ahead, and then then the disc, then the hoop. All right, and they all hit at different times. So why do you think this is? Shouldn't they all hit at the same time? I mean, if we're using our knowledge of potential energy to kinetic energy, UG should equal K, which means that MGH should equal 1/2 mv squared. And if that's the case, then V should be equal to the square root of 2GH. And that doesn't have anything to do with mass, and it doesn't have anything to do with shape. So what's going on here? Why is this a different situation? All right. This is a different situation because we're dealing with something that we've kind of fudged on in the past. The deal is that these things are rolling. All right. They are spinning. Okay. And since they are spinning, we have to account for the fact that they have some kind of rotational energy going on. All right. As far as which one gets to the ground first and why, you'll notice that the ones that have a solid mass seem to get to the bottom first, and then the one that had the hollowed out part got to the bottom last. And we'll talk about why that is in a second. So to start with, let's go to talk about what energy is in rotational form. So we know, hopefully we remember, that the linear form of kinetic energy, we just did it, was 1/2 mv squared. All right, but the rotational form, remember, is very similar. All these things have analogy. So the analogy for mass was the moment of inertia, so it's 1/2 times the moment of inertia. V, that analogy is omega, and so it's 1/2 I omega squared. Now remember that the moment of inertia was related to mr squared. And so for different shapes, you get different moments of inertia. For instance, a sphere has the sphere's moment of inertia is 2/5 mr squared. That's for the sphere. The moment of inertia for the disc, the solid disc, was 1/2 mr squared. And the moment of inertia for the hoop is just mr squared. And so basically what you can look at here is the one that has the least moment of inertia, the sphere, is the one that's the easiest to get to rotate. Therefore, it's the one that gets down the hill the fastest. That's what was happening. All right. So how does potential energy and kinetic energy relate now? Well, now, instead of just doing UG equals K, we have to add in the rotational kinetic energy if we're going to be dealing with that. So what ends up happening is basically you get mgh equals 1/2 mv squared plus mr, oops, my bad, plus 1/2 I times omega squared. Keeping in mind that I is usually going to have something mr squared. All right. Most of the time, I believe with you guys, they're going to give it to you. In Physics C, you have to have them memorized, but I think in y'all's case, they'll give you the I if you need to know the I. All right. So this is what was happening, and the reason that they went at different rates is basically some of the kinetic energy was being used to get it to rotate. The easier it is to get to rotate, the more you can put into kinetic energy. The hoop was much more difficult to get to rotate, so it lost some of its kinetic energy as it rolled down the hill. Okay, so to continue a bit, let's see. To continue a bit, let's talk about what it means to be rolling without slipping and slipping. And specifically, what does friction do in these cases? How does friction operate in these cases? If you're rolling without slipping, then friction is doing no work. That's important. So if there is a coefficient of friction, but you're rolling, there's no work being done by friction. So whenever you do your energy equations, there's no need to add in work done by friction. It doesn't matter whenever it's rolling without slipping. So what that means is if it's just rolling along, there's no slippage going on, meaning like there's no skidding going on. Like if you're in a car and you slipped, you might hydroplane or you might like skid. There's none of that going on, all right? If there is slipping, so like if a car skids to a halt or something like that, now friction is doing work. So friction is doing work, and you have to include it. So like whenever you do UG equals K rotational plus K linear, you have to include work done by friction in that equation, all right? So like whenever something is slipping, you do have to include it. Let's see. And this kind of brings me to where we've kind of fudged a little bit in the past. Whenever we've done any of these things in the past, all the way back to the beginning of the year, everything we've done has been assuming that it was sliding with a frictionless surface. And you may remember we constantly said frictionless surface. And that was because it was sliding and not rolling. And so when it's rolling, you have to incorporate a lot of different stuff. And so like whenever we did a thing where a baseball rolled down a hill at the beginning of the year, we said there was no friction. One of the reasons we said that is if there's no friction, it can't roll. And so it'll just slide down the hill. And so that's one, like basically that allows you to approximate what's happening with the baseball, similar to like how we stuck the air tracks on angles. All right, and then we put the gliders on them. Those slid down with no friction, and so you could basically, we were treating the ball rolling down a hill like that so that it was easier to do. This is the more correct way to go about these things. All right. Okay, so I'm going to spend a second discussing just a few little extras that you might want to be aware of. So, for example, I want to stress like something that we haven't really done a great job at going over, and that's that there is relationships between the linear velocity and the angular velocity, and there's also a relationship between the linear acceleration and the angular acceleration. And so basically that's the linear velocity is the angular velocity times the radius. The angular acceleration times the radius is the linear acceleration. And so one of the things you can do with that, for example, if you have a wheel, and I again apologize for not being able to draw a circle, and you know the radius of the wheel, and you know the omega that it has, let's say that it's 10 radians per second, you can calculate, let's say the radius is 2 meters, you can calculate the speed the wheel is moving along the ground. So if we say that it's got a omega that is clockwise, then we would know that the velocity would be 10 times 2, and so the velocity would be 20 meters, and it would be going this way, because the wheel would be pushing it that way. All right? So you can use that to figure that stuff out. Alpha works the same way. If you're accelerating at 10 radians per second squared, the acceleration would work the same way. Acceleration would just be 10 times 2. All right, and the reason that's important is sometimes, okay, so for example, whenever you're dealing with, let's say you're trying to get mgh and you're converting that into kinetic and rotational, kinetic energy, you have 1/2 mv squared, and you also have 1/2 I omega squared. Well, let's say that you don't know what your omega is, but you know what your velocity is. So one of the things you can do is you can rewrite this and say mgh equals 1/2 mv squared plus 1/2 I v over r squared. So you can like replace those variables, and sometimes that comes in handy. That's something that I wanted to make sure that you were aware of. And the final thing is I want to show you this. We have one more video. And what I'm going to do is I'm just going to show it to you because I want you to see that sometimes they do fall at the things can roll at the same rate. So things with similar moments of inertia fall at the same rate. And so we want to talk about what happens here. So I'm going to play this video. We're going to talk about it. So basically I'm going to drop, I'm going to drop 2 hoops at the same time. They're different sizes, but they're same basic structure. So 2 hoops, 1 disc, and a small disc and a big disc, and then a small sphere and a big sphere. And what you can see is that they all fall at about the same rate. All right, and so we're going to replay that. Big hoop, small hoop, fall at about the same rate. Big disc, small disc, fall at about the same rate. And big sphere, small sphere go down the hill at about the same rate. And so the question is, why do those things go down the hill at the same rate? Well, if you'll remember, whenever you drop objects, it doesn't matter what their mass is. Because remember that if you're dropping an object, if an object's falling, okay, if an object's falling, it's got a force of gravity down, which means that the sum of the forces is equal to mass times acceleration. The only force acting on the object is the force of gravity. And then basically that was mg equals ma. And it canceled the masses out. So it didn't matter what you dropped. If you drop anything, the mass cancels out and they fall at about the same rate. Now, there was some things you could get into like air resistance and stuff, but if you take out air resistance, everything falls at the same rate. Remember the feather in the hammer being dropped, or the feather in the bowling ball being dropped. So what's happening here? How are these things able to fall at the same rate, and why weren't the other ones able to fall at the same rate? Well, here's why. So basically, remember that torque is equal to I alpha, but it's also equal to the force times the radius. So what's the force acting on this thing? Well, if you'll remember, the force of gravity is going, let me get a different color. The force of gravity is going to be acting straight down, okay? Which means that the component that's pulling our objects down the hill is this one right here, the force of gravity in the x direction, and we got an angle right there. So notice that the force of gravity that is on the opposite sides, the force of gravity sine the angle, is what is pulling our objects down the ramp. That's also what's applying the force to the objects. So in other words, if we look at our objects, there's this force of gravity in the x direction pulling them down. That's providing a torque at a radius at their radius. Okay? And so what happens is you get I alpha equals mg r, or rather mg sine theta r. But remember I, it varies, but it's basically mr squared. So I'm going to start this with the sphere. So the sphere would be 2/5 mr squared alpha. Notice that the masses cancel out. And so what that means is if you have two spheres, as long as they're kind of uniform, if they're two solid spheres, they should fall at the same rate. They should roll down at the same rate because their masses cancel out. What about for the hoop? The hoop was mr squared. That was I for the hoop. And so mr squared alpha is equal to is equal to mg sine theta r. And again, your m's cancel. And so as long as you're a hoop, a uniform hoop, it doesn't matter what your mass is. You should kind of roll down at the same rate. And then finally, what about a sphere? Or sorry, what about a disk? A disk was 1/2 mr squared alpha, and you get let's see, mg sine theta r, and again, the masses cancel out. Some of you might have noticed this lingering r though. So you might be saying, well, doesn't the radius matter? Wouldn't that radius be an effect? Well, first of all, this r is going to cancel out because we've got an r squared on this side. Oops. And so what we end up having, and again, I'm going to do this in general, so I'm going to do it with the hoop just so we don't have to do it with the 2/5 or 1/2. But we end up with basically r alpha is equal to g sine theta. And then alpha would be equal to g sine theta over r. And so you may be saying, well, doesn't that mean that the acceleration would be different based upon a different radius? And the answer is yes, the acceleration, the angular acceleration is different, but remember they have different radiuses, so they need different angular accelerations to speed up faster. And what happens is since a, if you'll remember, a was equal to alpha r, the acceleration is just g sine theta. Whoops, let me see if we can write this somewhere else. The acceleration is equal to alpha r, and so the acceleration would be equal to g sine theta over r times r, and the r's cancel out, and they end up having the exact same acceleration down the ramp, which is convenient and also very neat. So they have the things that have the same formula for moment of inertia should have the same like acceleration down a ramp, but things that have different moments of inertia, different formulas for moments of inertia, will travel down those ramps differently. I encourage you to try this on your own. Make yourself a little ramp, try rolling things down it. You can roll batteries, you can roll cans of soup, you can roll some kind of any kind of ball that you have available, baseball, basketball, tennis ball, and see if any of those things have different rotational inertias, just to kind of get a feel for what I'm talking about here, because it's a little bit of a complex thing to be discussing and thinking about. More problems. So let me put in a couple of things here. So we've got, the first thing is just some things to try. So go, if you're at your house, and you all are, try this with some different things. So think about which one's easier to balance. You got a pencil, screwdriver, broom, meter stick, lollipop. Think about which ones are easiest to balance and which ones are harder to balance and where they're harder to balance. And I think what you'll find is if the bulk of the mass is away from you, it's harder to balance it. So this screwdriver should be easier to balance if you're balancing it from this point. This screwdriver should be easier to balance than this screwdriver. This lollipop should be easier to balance than this lollipop. And I encourage you to try this because it's kind of neat. It's a little bit counterintuitive, but the reason is because torque is equal to I alpha. If you have a bigger I, it's harder to get it to angularly accelerate. And since I is equal to, or at least related to, mr squared, the farther that mass is away from the center of rotation, the more difficult it is to get it to accelerate. All right, pull up a different problem. All right, Why would toy makers build children's tops with relatively large moments of inertia? Whoops. With relatively large moments of inertia, even though that makes it harder to get something to start spinning? Well, it's because it's also harder to get it to stop spinning. So you might remember that, like, is it the question we had at the beginning of the year? Is it like once you get a truck moving, why is it easier to keep it moving than it is to get it to move in the first place? And the answer is inertia takes over. And once inertia takes over, it's harder to get it to stop than it is to keep it moving. And the same thing is true with the tops. Once you get it spinning, even though it's hard to get it spinning, once it gets spinning, it's easier to stay spinning because it has a high moment of inertia, which is similar to, which in spinning terms is similar to having a large mass in linear terms. All right, and then let's see. Okay, I'm going to go to the next page just so we can have more room. So this one's an actual math problem. A solid 50 kilogram cylinder with a radius of 0.25 meters is rotating with an angular velocity of 60 seconds, or sorry, 60, well, that should be hertz, but 60 is 1 over a second. And so what I want to know is, what is the rotational energy stored in the cylinder? So this is just a simple kinetic energy. Kinetic energy is equal to 1/2 I omega squared. A solid cylinder is equal to, the moment of inertia is equal to 1/2 mr squared. And so the kinetic energy would be equal to 1/2 times 1/2 50 times 0.25 squared, all times 60 squared, because 60 is our omega. And so if we type that in, we get 0.5 times 50 times 0.25 squared times 60 squared, and we get a kinetic energy equal to 2,812 joules. And that's the rotational kinetic energy. Again, this term right here came from the moment of inertia, which was right here. Now, if that energy could be entirely used to lift the cylinder, how high would it go? Well, this is just a old kinetic energy converting into potential energy. So we have 2,812 joules, and we're going to convert that into potential energy. So mgh, 50 times 10 times h, and we're going to divide that by 500. So it would go 5.625 meters into the air if you can convert it all into potential energy. All right, let's try another one. Let's see if I can pull up another one real quick. All right, let's try this guy. So on this one, we've got two shapes shown have the same mass and the same diameter and rotational speed. Which is true and why? All right, so do both have the same angular inertia because the speed is the same? Angular inertia, remember, angular inertia is going to be how hard is it to get it to stop, all right? So how hard is it to stop it spinning? So both have the same, okay? The thin wheel has more angular inertia because its mass is concentrated near the axis of rotation. Or the thick wheel has more inertia because its mass is distributed farther from the axis of rotation. And the answer to this one is indeed C. Okay, so what happens is C is what you sorry, my bad. C is the answer because I is equal to mr squared, or at least related to mr squared. So the farther you can have that mass from the axis of rotation, from the radius, the more inertia you're going to have. Sorry, I stumbled there. Okay, let's see. Let's get one more in here. This one's going to be a bit tricky, okay? So I need you to hang with me, okay? So we've got an engineer wishes to modify an existing flywheel design so he can store more rotational energy. Which of the following changes will increase the rotational energy by the largest factor? Okay, so the original design calls for a solid 50 kilogram cylinder with a radius of 0.5 meters and a rotational velocity of 60 seconds, 60 inverted seconds, or 1 over seconds. We could call that 60 hertz. All right, so let's make up a formula for the rotational energy initially. So the rotational energy initially is going to be equal to 1/2 I omega squared, okay? But the I for a solid sphere is 1/2 times 1/2 times 1/2 mr squared times omega squared. Okay, so the deal here, we got to remember, whenever you're dealing with stuff like this, you change what it tells you to change, and you just make everything else 1. So this is our generalized formula, all right? We're going to change what it tells us to change on each one of these, and then everything else is going to be 1. Whatever happens is what the factor we will increase our rotational energy by. So if we increase the radius to 0.75, so basically what I'm going to do there is the radius would be multiplied by 1.5, okay? So what happens if I multiply the radius by 1.5? Well, basically everything else, I'm only concerned about the radius, so I would be squaring the radius. So what happens when you square 1.5? You would get 1.5 squared is 2.25. So if I do that to the radius, I'm going to increase my kinetic energy by a factor of 2.25. 2.25 is what I'm going to increase it by. All right, what if I increase the mass by 100 kilograms? Well, in that case, I'm doubling the mass. So what is that going to do to the rotational kinetic energy? Again, I'm going to keep everything the same that I'm not changing, and I'm just going to double the mass. Well, if I'm doubling the mass is not squared or anything. So if I double the mass, it should double the rotational kinetic energy. Okay? We're going to skip C for just a second. Let's come back to that. We're going to double the angular velocity. So if I double the angular velocity, notice that the angular velocity is squared. So if I double omega, omega is squared. So 2 squared, I'd be quadrupling the kinetic energy. All right, so I've got to look up what the moment of inertia of a hollow sphere is, hollow cylinder. Moment of inertia for a hollow can't spell, hollow cylinder. Okay, so the moment of inertia for a hollow cylinder is mr squared. So basically, whenever you do this, you've got to, the I is now mr squared, so you're dropping out the half, and we're also going to reduce the mass to 25 kilograms. So basically, what I'm doing is I am halving the mass and then taking off a half from the beginning part. And so what ends up happening is basically my new moment of inertia, the new thing that I'm going to plug in here, would look like this. The new thing I would plug in here would be 1/2 times mr squared times omega squared. But notice that I'm halving the mass as well, so I've got to put that half back in there, and so nothing would happen to the rotational kinetic energy if I did that. And so I would end up with a rotational kinetic energy that was the same. And so the one that would do the most would be doubling the angular velocity. All right? So I hope that helped, and if anybody has any questions, feel free to email either me or Ms. McCombs.